All right. Now we come to the last section of the whole semester. That is the dot product of vectors. So let's wrap it up. Before we talked about a product of two numbers. Okay, 2 times 3 equals 6. That's very easy. Then we talked about the product with a vector, but if you try to recall, we do have one vector and one number. So for example, if you have a vector v, and you want to calculate 2 times v, which is a number times a vector, you basically just rescale the size but keep the directions. Now, of course, we have defined addition and subtraction of two vectors. Then naturally, we should also ask, can we do the product of two vectors? A vector times a vector. Okay. How do we define it such that this one has a certain kind of geometric or maybe algebraic meanings, which is convenient for us to study certain kind of problems? And it turns out there are multiple ways to define a vector times a vector. It's not unique. And each one is useful under a certain kind of situation. And what we want to talk about now will be one type of vector times a vector, which is called the dot product. Later, you will also learn what you mean by a cross product. That's for later. Okay, each one give you some meanings. This one will give you the area of the parallelogram, but that's for later. So to differentiate them, we have to define times using different symbols. So next time for vectors, when you see something like that, just keep in mind, whenever you see a dot, you see a multiplication. For numbers, they are the same. But for vectors, this symbol becomes very, very important. You cannot simply just write as before. For example, if you have x times y, you just simply write xy because dot, cross doesn't make a difference. But for now, you have to be very specific to write them out, to tell people which kind of product you are looking for. Okay, so let's talk about this dot product. Represented by the symbol dot. And we will only do it with respect to coordinates first. So suppose we have one vector. Suppose we have another vector. All right. Now, A dot B is defined to be A1 times B1 plus A2 times B2. Now keep in mind, before these are two vectors. Each one has two coordinates, so together we have four numbers, A1, A2, B1, B2. The right-hand side will be the multiplication between the numbers. That becomes number multiplication, so you can write down this dot, or you can just simply erase it, and there's no confusion, because it's a number times a number. Either way, once you finish, this one becomes a number. So the product, the dot product of two vectors give you a number. Okay? Very quick example. What is 1, 2? Dot 3, 4. That is going to give you 1 times 3 plus 2 times 4. So y, x go with x, y go with y. You multiply each one, but when you finish, you take the sum. No, 11. Okay? 1, 2 times 2 negative 1 give you 1 times 2 plus 2 times negative 1, which give you 0. Okay, and keep going, you can have all kinds of numbers. So from here you can see the dot product of a vector can be positive, can be negative, and can be 0. Later we will illustrate what the sign means, positive, negative, 0. What does it mean? But for now, this is the definition. Okay. Second, why is it useful? I mean, you don't have to define the product in this way, but if you define the product in this way, you will have certain nice properties. Okay, what is the property? Well, number one, if you take a vector, you dot yourself, what's going to happen? It's going to be A1, A2, dot A1, A2, and like we said, you multiply the x, you multiply the y. But now your x are the same and your y are the same, so if you multiply them, it's the same as squaring them. But what is the value of this one squared plus this one squared? That is going to be the magnitude of A, but squared. Okay, so that's the first property. If you dot a vector by itself, it's equal to itself squared. Okay, but keep in mind, we will never write down something like this. Okay, when you have 2 times 2, you know it's 2 square. When you have 3 times 3, you know it's 3 square. So this square means you multiply something for multiple times. Okay, but for vectors, you cannot simply do that, because if you do that, I have no idea what do you mean by times. Because certainly I can have dot product, I can have cross product, and maybe other products. So don't write this thing down. If you want to write a vector times itself, you always write the whole thing out and tell people what you mean by times. For this case, we do have dot product. However, on the right, you can write it because this is a number. And for number, you square it. It doesn't matter if you write cross or dot, they're all the same multiplication. Okay, so be careful. So next time you say, hey, 1, 2. Here is a vector, and you want to find how long this is. Well, one way to do is go with the formula. It's the square root of 1 square plus 2 square, which is square root of 5. All right, but there's another way to do it, which gives you 1, 2, dot with 1, 2, because, and then squared, which is again the same thing. So that's the first nice property of dot product, which should make sense, right? You times yourself should be yourself squared. But when we say yourself, we mean the magnitude squared. The direction doesn't matter anymore. Okay. Second, some algebraic properties. Number 1, A plus B equals B plus A, and not B, dot. So we don't have to worry about which order are we dotting two vectors. A dot B is the same as B dot A, which is very easy to prove. The first one is going to be A1 B1 plus A2 B2, but the second one is going to be B1 A1 plus B2 A2. So you basically switch the order of B and A in terms of x and y coordinates, but you know these two will be the same because they're numbers. These two will be the same even though you switch the order. So if sum together, they're still the same. That is nice. Later you will see when you do cross product, you don't have this property because they have certain meanings. Okay, so that's the first one. Very nice property. Second, if you have a number, let's write them all out. You have a number times u dot v. It's equal to the number times u first, and then dot with v. What do you mean? It means if you have 2 times 1, 2, okay, dot 3, 4, you have several ways of computing it. Okay, the first way is you keep the 2, you do, okay, which is 2 times 11, which is 22. Or you have an alternative way. That is, this one equals to 2, 4, which means I multiply the 2 with the vector first, ignore the dot product, and then do 3, 4. After that, we will have 2 times 3 plus 4 times 4, which is different from what we had before, but now you can see you still receive the same number. So which means if you want to double the product, it's the same as double one of the vectors, and then do the dot product. Okay? Number 4, u plus v, a plus b dot c equals a dot b, a dot c plus b dot c. This is another nice property, which means you can distribute. Okay. Now you can prove this if you write down a equals this, b equals this, and the c equals this. Okay. I will urge you to do this by yourself. Okay. Calculate the dot product on the left, which give you a1 plus b1, a2 plus b2. That's where you do the addition first, then do the dot product. Okay, which give you a1 plus b1 dot c1 plus a2 plus b2 dot C2, and then finish this to try to see, okay, it's the same as what's on the right. You do the dot product, each one with C first, and then take the sum. So this one satisfies exchange law, which means you can switch the order, A dot B, B dot A. This one also satisfies, if you multiply that thing with a number, the number really doesn't make a difference. You can move it anywhere. Finally, you can have the distribution law, which is very, very important. So when you do the complicated computation, complicated algebraic manipulation with dot product, it's basically safe for you to do everything we have done before with numbers. You can distribute. That also means you can factor or combine things. And finally, that means you can exchange the order. Okay. Very quickly. Are they the same? Okay, so just as example to show you, there are certain laws that with number applies. Okay, but there are certain laws with number that doesn't apply. If you take a closer look with this is a number times a C, right? Because A dot B is a number. The one on the right is A times a number. And what do you mean by a vector times a number? That means I'm going to rescale, say, C, and I'm going to rescale A. So no matter what, this one will be in the direction of C, because you keep the direction. This one will be in the direction of A. So no matter they have the same size or length, they will not have the same direction in general. So these two are not the same. But for numbers, this clearly is true. Okay. So even though you kind of feel safe, but again, keep in mind, you cannot have certain kind of manipulations unless it's guaranteed by the rule. For vectors, for dot product, a lot of nice rules apply. Meanwhile, watch out for some rules like this. Make sure you can have some foundations every time you write down some manipulations. All right. That's everything we have. Okay. Now, of course, this is just a simple manipulation. We wonder why we want dot product. Why is it useful? So it's called the dot product theorem, but I would just say the geometric meaning of dot product. So what does dot product really give you? What does this number mean? This A dot B. Let's try to show it or prove it. Okay. Let's consider A minus B. Okay. Let's consider A minus B dot itself. Now, number one, remember we can distribute vectors, so it's the same as what we did before with algebra. You factor everything, you FOIL everything out. Now you realize this is what? A dot itself is the length of this. I will move this one here. Okay, B dot B. Now I'm going to minus 2 A dot B. Okay, so A minus B dot A minus B, by the way, equals A minus B squared. So I will just write down that. Okay. So by using the properties of dot product, if the dot product is defined in this way, then this expression is true. Okay. But what does it mean? Now it's interesting. Take a look at what's going on. If you put A here, if you put B here, what is A minus B? A minus B is this. Okay. Now, if we don't worry about vectors, we only look at the length of the vector, which is the magnitude. Can you realize this is nothing but solving a triangle? You have 3 sides. Okay, every single thing here is not a number anymore. It's not a vector anymore. It's a number representing the sides. Therefore, you can have a certain relationship between these 3 sides. That is which is coming from the law of cosine. Okay, if you want to see it, you can just simply see this is c squared equals a squared plus b squared minus 2ab. Cosine theta. It's just, c and a and b in the law of cosine representing the length of the size. So each one now is represented by the corresponding magnitude of the vectors. Okay. Moreover, theta is the angle between these two vectors. They start together. Theta is the angle in between. Now if you compare these two, the first one is what you get from the properties of the dot product defined in the first way. That is, this equals that. Here you get the same thing equals that. Now let's compare them. The first term, they match. The second term, they match. And they should match, right? They are the same thing. Therefore, the third thing has to match. The third thing has to match, which means this has to equal to that. Otherwise, either dot product property fail or the law of cosine fail. But we know they are both true. Then we have to admit from the law of cosine. Therefore, we have the geometric meaning of A dot B. It gives you A, it gives you B, it gives you cosine theta. That is the most important property of the dot product. This is why we need it. All right. Now, no surprise, some properties we had before. Number one, we said, okay, A dot itself, okay, should equal to this, right? But now if you look at the expressions, of course, A dot itself equals what? Equals A dot cosine theta, where theta is the angle between A, which is 0 degree, which is 1. So there, of course, it's this. Now, A dot B equals B dot A. We know it's a property. But now if you think about it, well, A dot B will be the magnitude of A times magnitude of B times cosine theta. B dot A will be simply switching the magnitude of B and A, which are switching numbers. So of course they're the same. Okay, so we have all the nice properties we had before. That is great. Number 3, if you think about 2A dot B equals 2 A dot B, now it seems right because this A dot B, and now what happens is you can either do the A dot B and times 2, or you can double the size of this one and times B again. And then you simply have a 2 here, which changes the magnitude of A. Okay, so that's nice. All the properties before now make sense. And this is a very useful fact, even though maybe you haven't seen it. But let's try several examples. Okay, you will see why this one is powerful. Okay, because you can do law of cosine, which is very useful, but this time you can do it in an easy way. The first one. A, 1, 1. B, 4, 2. C, 2, 5. Okay, so we have a triangle. Now, I don't know why you want this triangle. Maybe you're trying to do some constructions or whatever. But here's the beautiful thing. I want to ask you, how big is this angle B? Okay. Angle B. Well, how do you do it? If you know A, you know B, you know C. If you don't know the dot product, maybe you can calculate how long AB is because you can do the distance formula, so you know the AB. You can calculate this one. You can calculate this one. So you know the 3 sides, and now you want to know one angle. What do? You use the law of cosine. So that involves finding the 3 sides, which is a lot of work, And then you do the law of cosine, which is a lot of work. And then you got cosine, and then you do the cosine inverse, which is very complicated. Okay? But now, forget about it. B is the angle between two vectors. Which two vector? BA and BC. Make sure they start together. Okay? So you have BA and BC. Now what can you do? You can say then BA dot BC is going to equal to BA times BC. Only the magnitude, then times cosine B. Which means if we can find all these numbers here, 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 and here, we will be able to find cosine B. Okay? But can you find all these things here? Well, as long as you can find the vectors BA and BC. Okay. Then you can calculate the dot product and you can calculate the magnitude. Can you find BA and BC? Piece of cake. Then BA is the ending minus the starting. So it's 1, 1 minus 4, 2, which is -3, -1. If you don't believe it, how do you get from 4, 2 to 1, 1? You go left by 3, you go down by 1. BC equals C minus B, 2, 5, -2, 3. Okay, then what is BA dot BC? That's going to be -3, -1, dot -2, 3, which give you -3 times -2 plus -1 dot 3, 6 minus 3, which is 3. Okay, that's the one. But how long is BA? That is going to be square root -3 squared plus -1 squared, which is square root of 10. BC is going to be square root -2 squared plus 3 squared, which is square root of 13. Therefore 3 equals square root of 10 dot square root of 13 dot cosine theta. If you plug in everything into the original definition of dot product. So what is cosine theta? Whatever that is. Okay, theta equals, remember, we just need to do cosine inverse, because cosine theta give you only one value between 0 and pi. It's a triangle. For sine, you have two possible values. Okay, so cosine inverse roughly it's gonna be 1.3. Okay, pay attention when I do things like that. It's gonna be radian. For degree, you probably have something a little bit bigger, roughly like 75 degree. Roughly. Okay. Did we use the law of cosine? Not really. All we did is number one, trying to find the vectors. Super easy. A point minus a point. Number two, finding the magnitude of a vector. Super easy. Pythagorean theorem. Number three, finding the dot product. Well, super easy. Once you know the two vectors, there's nothing easier than this. But when you finish, according to this nice formula, you will be able to find the angles. That means you can basically find any angles in here, which is super nice. So even though the formula is like that, but actually very commonly we are going to use it in this way. That is, you divide these two on the other side because you want to find the angle. So this one make finding an angle super easy. Okay? Maybe you still don't see the advantage. You can still get it from the law of cosine, but imagine if this is something in 3 dimensions. Okay? You have something like that. I have to say, hey, I take the midpoint here. you know? And then I draw an angle, I draw a line from here to here. Okay, then I draw another line, I draw another thing here. I draw the inside the cube. So I got these two things. Okay, the midpoint of the other two sides, okay, right in the middle, starting from one side of this, and I ask you how big is this angle. Well, it's going to be hard, number one, for you to find all the sides because you cannot do it in one step. Okay, you need to have involve multiple triangles. Second, after that, you need to use the law of cosine. But if you use vectors, it's super easy. You just need to find this vector and this vector. We're not going to touch it, but you can kind of imagine each one is going to be a vector in 3 dimensions like this. Something like that. Okay, I made the numbers up, of course. And then to take the dot product is super easy. To find the length is Pythagorean theorem. You can do it in 3 dimensions, like a charm. So this is super, super convenient. Even for now it's convenient, but in 3 dimensions, it's definitely better than the law of cosine. Okay. Second, you don't have to worry about law of cosine. It's nice because sometimes one triangle is not enough. For example, let's still take the flight. But this time, let's drive like crazy. Okay, so we first start from here. We drove to north. Let's take easy ones. Okay, north. Okay, 30 degrees, 400 miles. After that, we drive east. We fly east. For 200 miles. Okay. After that, we fly how much? I don't know. Then we fly 45 degrees towards this direction for another 100 miles. I better be careful. They're not parallel, so just to let you see. So no, try to draw a more extreme. Let's do another 75 miles. No, I don't want that. Probably 100 miles. Okay, and then finally, I fly in the direction of 60 degrees for another 150 miles. So I'm going crazy. I fly for a certain distance for every single part. Now my question is, which direction is this one from here? If you trust my drawing, the only information you get for now is probably it's going to be south, east, but this degree is missing. Sounds good? So that's super difficult. Okay. All right. Now what we want to ask is what's the angle between the initial? So what's the angle between the initial and the final destination now after you draw it for 4 part of journey? Okay, you want to find this angle. How do you do it? Can you see? Number one, if you do it, you will first do the law of cosine in this triangle. Okay, finding all the sides and everything, and then you do the law of cosine in this triangle. Then you do the law of cosine in this triangle. Finally, you can figure out these 3 angles. You sum them together because you have at least 3 triangles involved. So if you want to use the law of cosine by drawing 3 different triangles and use the law of cosine for 3 times, be my guest. Okay? But for now, you don't have to. Why? Because we have dot product. You just want to find cosine theta, right? Okay, what is cosine theta? Cosine theta will be the angle between 2 vectors. The first vector And if I name it, this is B, this is C, this is D. Okay, it's gonna be the vector, the angle between two vectors, which is A, and this red vector, which is nothing but A. I'm going to call it X, which is nothing but A plus B plus C plus D. Right? Okay, so basically this one equals A dot X divided by A dot X. Why? Because of the law of cosine is hidden in the definition of dot product. Okay. So what's your job? Your job is try to find A, which you already know, and to find X, which you can know by adding all the four vectors together. Once you have that, you can do the computation. So I will just do it really quickly. Okay, you can check your mind work later. A. Okay, it's 130 degrees. So horizontally, you're going 50. Vertically, you're going to 50 square root of 3. Okay. Now you're here. Okay. B, you're going east for 200. So 200, 0. Okay. C is going to be 45 degrees with 100. Okay, so what you got is negative 50 square root of 2 times cosine 45 degree and 100. You do that by yourself. And negative 50 square root of 2. D. Okay, going this way. And this is 150, if I remember correctly. Okay, so that is going to be 60, which give you, this is 75. This is 75 square root of 3. So 75 square root of 3, negative 75. That's the four vector. All of this together give you X equals A plus B plus C plus D, which is the vector pointing directly from the starting to the ending. Okay. And you simply just need to put all the X together. 50 plus 200 minus 50 square root of 2 plus 75 square root of 3, and Y is going to be all right. We will use a calculator to make our life easier. So the first one is roughly typo. 50 plus 200 minus 50 plus this. 309. Okay. And the other one is going to be negative 59. That would be the vector of the red vector. That would be the coordinate of the red vector. Okay. Then, you know A. You know X. Now you just want to find the cosine theta. It becomes super easy. The top is the dot product minus. Plus actually 50. That's the dot product. At the bottom, you just need to divide by the magnitude of each vector. Whatever this number is. Okay. Now let's clear each of them. This is 100 square root of 309 square plus 59 square. That is roughly 314. Okay. On the top you have Okay, 1, 0. Okay, then theta equals cosine inverse, which is which is 1.24, roughly 71 degree. Okay, I strongly suggest yourself to do the whole process by yourself for at least once to appreciate when you have a very complicated problem, even though transferring the law of cosine to dot product just save you one small step. But if you have a lot of steps to do, it saves you a lot of trouble. Because as you can see, the more vector add to it, it doesn't make things more complicated. But for the law of cosine, it's going to be super confusing. You need to constantly remind yourself which triangle are you talking about, which angles are you talking about. Okay, but for vectors, you can simply forget about all their locations. Just keep writing down the algebra, and it will be working. All right, so that's the first big advantage of the dot product. It handles all the angles. Okay, now what can we do? Well, with all these, we have another interesting fact. You know, A dot B equals A dot B dot cosine theta. Okay. That can tell us a very interesting thing. That is, A dot B can be what? Can be bigger than 0, less than 0, or equals 0. Okay. But if you look at the right-hand side, this is the magnitude of a vector. It's going to be non-negative. You're not going to have something with a length of 3, okay? A negative 3. This is going to be positive all the time, except B is a 0 vector. Therefore, if this is positive, it's the same to say cosine theta is positive. Okay. But if cosine theta is positive, that means what? That means AB has an acute angle, okay, which is between 0 and 90 degree. Or let's say it more carefully. 0 less. Okay. Similarly, if it's negative, these two terms are positive. Therefore, the only chance is cosine theta is negative. That means 90 degree is bigger than theta, is less or equal than 180 degree. Okay. Now, what do you mean it's 0? The two possibilities. Number one, A equals 0 or B equals 0. So you don't have a length. That's possible. But most of the time, you should have cosine theta equals 0. That means theta equals 90 degree. That means A is perpendicular to B. So what's going on here? That tells you this give you A dot B is positive. This give you A dot B is exactly 0. And this give you A dot B is negative. Because simply that just tells you the sign of the cosine. So quadrant 1, quadrant 2, and exactly on the y-axis. Of course, that's working. But now, what you can see is, you can easily tell if AB is roughly in the same direction, or if AB is in the opposite direction, or if AB is totally uncorrelated. So in statistics, later you will see this is exactly the definition of correlation. Okay, so what do you mean by in the same direction? Well, this means in the same direction. But what about this? Well, you're not totally in my direction, but you're still helping. So I'm not going to say you are in the same direction, but roughly you're pointing towards the same trend, even though not completely. Okay, while this one is certainly not helping. They're going against each other, not completely against each other, but a little bit against each other. But for this case, you go your way, I go my way. And there's no intersections between these two. That's when you can decompose everything. Okay, so just looking at the sign of A dot B, you can roughly have the idea of the directions between two vectors. And of course, we are very interested in this because it's very useful. A dot B equals 0 if and only if A is perpendicular to B. Now be careful here. There is another possibility that A may be 0 or B may be 0. But now if we just add 0 is perpendicular to any vector, then this statement is no trouble. Okay? Even if you have a 0 vector, it's still perpendicular between each other. Okay? That is a very important property to have because perpendicular is very, very important. I will show you some examples, which is fantastic. Okay? Now, I think everybody has seen these examples before in geometry. That is, if a parallelogram, and let's not do that. Say, if A plus B equals A minus B, okay, then what? Then A is perpendicular to B. Let's try to show or try to prove this. Okay. By the way, this is for fun. We are not going to test this, but I just want to let you know that, to show you that why this is amazing. Okay. So if you couldn't do this by yourself, it's fine for now. If this equals that, we square it, it's still equal, right? All right. Then that means A plus B dot A plus B equals A minus B dot A minus B by the definition of dot product. But then what we can do is we can distribute. We will have one term like that. We will have one term like that. And we have done this before, so I'm just going to write it down. We are going to have A dot B and B dot A, but they're the same, so twice of them. Okay. So if A plus B and A minus B and A minus B share the same magnitude, you square both, you will have this equation, and then they are the same, so they cancel. You will have a conclusion that is A dot B equals negative A dot B. But remember, you have a number. Equals itself, taking the negative sign. That implies A dot B has to be 0. Therefore, this implies A dot B equals 0, and A dot B equals 0 implies A is perpendicular to B because it implies cosine theta is 0. Therefore, A is perpendicular to B. Sounds good? It's very easy. It's almost the same as when you do the numbers. A plus B squared equals A minus B squared must imply A dot B equals 0. Right? It's the same algebraic expressions, so it's very easy to write this proof. It's almost boring to write this proof. Okay? But now let's see the magic. This is very easy. But the surprising part is this is very useful because you need to realize what it's talking about. Now if you draw two vectors A and B, do you know A plus B? Well, we have done before. You do the parallelogram law. A plus B is nothing but the diagonal of the parallelogram. What is A minus B? A minus B is the other diagonal of the parallelogram. What do you mean by A plus B equals A minus B? That means you have a parallelogram which has two diagonals, and these two diagonals has equal length. Okay. This implies A perpendicular to B, simply is saying a parallelogram with equal diagonals is a rectangle. This is some conclusion you get it from high school, or maybe, I don't know, junior high geometry. How did you do it? Probably you did some similar triangles, parallel angles, all kinds of geometric properties you have to memorize. But now if you just use vector, do you realize everything you have about shapes suddenly reduced to algebra? That's interesting, right? That's beautiful. Okay, can you do the same thing? Let's try one more. I believe a lot of people know this. A parallelogram with perpendicular diagonals is a diamond. Okay, what it says is, okay, you can have all kinds of parallelograms, and there's no guarantee they will have equal perpendicular diagonals. But if they have, if this is 90 degrees, then this is a diamond, which means all the four sides has equal length. Okay, let me say it again. If this parallelogram has perpendicular diagonals like what I said here with 90 degrees, then all the four sides are the same. For a general parallelogram, you don't have that. You have this side and this side are the same, the opposite side are the same, but the four sides are all the same. That's what I'm trying to say. You have seen this before in junior high. But now with what we just did, I think you can translate this one into the vector language. Okay. Instead of prove this or saying this, you can say if a plus b, which is one but diagonal, is perpendicular with a minus b, which means a dot a minus b equals 0. That's how I translated the first one. Okay. Then what? Then you have a diamond. What do you mean by that? That means a and b have the same length. Then not the same direction, so you cannot simply say a equals b in terms of vectors, but the magnitude will be the same. So to say everything like this is equivalent to say something in the vector language. Then to prove this one is the same as proving this same thing in the vector language. But can you prove it? Now if you take a look, it's super easy. That means a dot a minus b dot b equals 0. That means a square equals b square in terms of magnitude, properties of dot product. Now you take the square root, but you know they're both positive, so done. It's basically trying to say if a squared equals b squared, then a equals b, given that they're both positive. Super easy to prove. No similar triangles, no anything you use in geometry. As long as you translate it into vector, you can have a whole new language to say the same thing you said before. This is fantastic. Okay, we will stop here. You can have more and more and more. You can basically go back to everything you learned in junior high geometry and try to translate them into the vector language. You will find all the geometry become algebra, and it become as simple as doing a lot of algebraic identities. And all you need to know is just the simple laws about, you can exchange the order of dot products, you can distribute, and that's it. All right. Now, the last thing. Actually, the last thing and application of the last thing, which is called projection. So we did number 2. So number 3. Now we know what dot product can do. Let's see another big applications of dot product. Projections. Okay. The idea is quite simple. Okay. If you have a light pointing to the ground, if you have a roof or cover or whatever, The projection is nothing but, the shadow. Okay, so if the projection is nothing but this. We have all done this before. And if you know how long this is, okay, if you know the angle here, you will be able to actually calculate the length of the shadow using trigonometries. It's simply theta. You have this one times the cosine theta. You got this. Okay, great. But now we want to change things a little bit. That is, we not only want the projection into the horizontal direction, actually we want to be able to pick the direction which we want to project the thing onto. For example, you have a roof, but this time you have a light coming this way. Okay. Moreover, you have a roof built on an incline with a 15-degree here. Now I'm wondering, what's your projection here on this incline instead of on the horizontal thing? And remember, unless you want to go over all the trouble to find what this angle is, otherwise you are just going to go with what you have here. Okay? Then we kind of extended the definition of projections. Not only you can project on the horizontal or vertical, which is actually the easiest case. What we can do is we can actually pick any direction and project something onto it. Okay? So it narrowed down to the projection of a vector onto another vector. So you can say the thing here is nothing but the projection of this one onto the vector B. Okay? So that's the first thing we want to talk about. Let's try to make the definition clear. If this is A, if this is B, I draw it to be horizontal. It doesn't have to be horizontal. Okay? Then the projection of A onto B is going to be this part, which is again the shadow. And you're assuming the light, the projector light, is coming from a direction which is perpendicular to B. So the light goes this way. That's how you get this. All right. Question 1. Oh, hold on. And then the notation is given by projection of A onto B. So this is the one you want to project onto. This will be the original one you will start projecting. Okay? Then question 1. Are they the same? Now if you draw it, this is the projection of A onto B. Let's use different color. Okay, so I draw it out. Projection of A onto B. Now what do you mean by projection of B onto A? That will be you have a light coming this way, which is perpendicular to A. So this is the projection of B onto A. You see the difference? So in general, they are not the same unless you have a very rare case. They just to become the same length. Even they become the same length, they are not in the same direction. So in general, they are not the same. That means the order matters. So be careful with which one you put on the top, which one you put on the bottom. Okay, so that's the first thing. Okay. Second, if you're talking about the projection of A on B, okay, no matter how you do the formula, okay, your question becomes, B only provide you with a direction. So the length of B should not matter. I will give you some examples. Okay, So let's say we have A. You want to project that thing on this B. Okay? You have A. You want to project that thing on this B. From here, you can see you have the same A, but you have different B in both cases. But now I want to ask you, what is the projection of A onto B? Well, you do this. And your real vector should have a length like this, because it only has something to do with A. A longer A will give you a longer shadow. Still okay? But the length of B should really not matter. As long as you're pointing into the same direction, you take a smaller one, you take a longer one, it really doesn't really matter, because what really matters is the length of A. Okay? With that in mind, let's do the formula. Okay. So let's see, how do we do it? How do we do it? This is A, and clearly this is the vector we're looking for. Okay. By the way, this is theta, and we would like this one to be theta because that's the angle between two vectors. You can get it if you want. Okay, using the dot product. All right, so we're trying to find this vector. To find a vector, you only need two things. Okay, the first one, magnitude. How long is it? It's going to be this one times cosine theta, according to the right triangle trigonometries. Great. Number two, what's the direction? The direction should be in the direction of B. Okay? With that, can you do the formula? Well, easily. Number one, what is this? Actually, we start from here. What is this? This is going to be A dot cosine theta, okay? Which is, no. And beautifully, they cancel. Okay. From here, you can see these two things cancel each other in terms of length. Therefore, the length of B doesn't matter. It's only involved in the length of A. So beautiful. Of course, and cosine theta. So this will be the vector. And this is still a number. How do you make sure this number goes in the direction of B? You just times B. Okay. Meanwhile, you want a vector in the direction of B, but have the length you desire. You better get rid of the length of B first, and then times the thing you want. For example, if you have some vector with a length 2, you want it to be length 3, what do? You times 3/2. You first get rid of 2 to make it a unit, so now you have 1. And then you times the length you want, you will have whatever length you want. So from here you can see, you can either view this as rescale B and then get rid of the effect of B, or you can simply think about this one as a unit vector in the direction of B. So only the direction matters, and really the length doesn't really matter. So you can multiply it with the length you want. You get exactly the direction and the length you want. So together, if you want to clean things up a little bit, this will be the formula. Okay. Note, this is a number. A dot B is a number. B squared is a number. This is a vector. So together, it's going to be a vector. Moreover, it's going to be in the direction of B. All right. Personally, actually, I prefer the first formula. So because that gave me such a clear idea. I'm timing some length in terms of unit vectors. But which formula you want to go, it depends on you. Okay? But we also want to define the component of A onto B. This is just some terminologies, okay? Which is nothing but the magnitude of your projection, which is nothing but this which is just the first part. So do you have the projection or do you have the component? It really depends on, are you just caring about how long the vector is, or do you also care about the vector? So same thing. Okay, now we have two formulas. How do we do it? Let's see some examples. Let's say we have a vector v equals 1, 2, find, and b equals I. So find component v onto I and projection v onto I, whichever way you want. Okay, so now v equals what? 1, 2. I equals what? 1, 0, 0. Okay, so what is the component of v onto I? By the formula, that's going to be v dot I divided by I, which is 1 times 1 plus 2 times 0 divided by 1 squared plus 0 squared, which gives you 1. So the component of v on I is 1. What's the projection of v? Use the formula. Okay, dot I again. Okay, the first one we have already computed. Now you have 1, 0 divided by square root of which is 1 times 1, 0, which is 1, 0. Okay. So here the component is 1, which only give you the magnitude, but the projection is going to be 1, 0, which give you the exact vector you're looking for. And moreover, the magnitude of 1, 0 is going to be 1. So what did we do? We basically took a vector and we say, hey, what's your projection in the horizontal direction? So according to our computation, of course it's 1. It's just going to be your x component. Okay? If you care about the length, it's going to be your x coordinate. If you care about the vector, it's going to be the x coordinate in the direction of the positive x directions. So that's what we got. For this, we technically do not have to define projections if we only care about horizontal and vertical, because it's so nice. But now things become interesting. Let's go to the incline. This is 30 degrees. Okay, we have a vector. Okay, this vector is given by 2, 3. Okay, the incline has 30 degrees. Now the question is find the magnitude, or just say find the length of the shadow. On the incline. You want to know how long this is. All right. So now our job is try to figure out we're doing what. So number 1, we're doing a projection for sure. It's going to be the projection or component. You want to find the length of the shadow, then you are looking for the component. You don't care about the direction, you care about how long it is. All right. The component of v, of course, projected on which vector? On a vector A, where A is the vector going in this direction, which represent the incline. So what we're trying to do is trying to do this. Okay. To do that, we need to find A, and we only know one thing about A, that is the direction. We need the magnitude of A also, but the good news is the magnitude doesn't matter, so you can make the magnitude whichever way you want. Therefore, just make up a vector which points to this way. Okay, if you take the magnitude to be 1, this one certainly work. If you check the unit circle. Or you can make the magnitude to be 2, then this one will work. Okay, you can make it anyway, but my question is, okay, whichever way you take really doesn't really matter. So for me, I think this one without 1/2 is better. So I would take this one. But if you take the same thing here, it will give you the same component. Again, the length of A doesn't really matter because you're going to divide it either way. Okay. All right, so if I know V equals 2, 3, my A equals this, then the component of V onto A is V dot A. Make sure you know which one to divide. Okay, it's always this one on the bottom because its length doesn't matter. Divided by square root. That's it. No need to draw right triangles, no need to use the law of cosine, play with angles, nothing. As long as you find the two vectors, the projection is going to be this way. All right, try some more examples in your homework. As long as you memorize the formula, the computation should be okay. But I think what's more important is actually to ask yourself, why the formula look like this? Okay, and go through the process, you will see, well, the formula kind of makes sense. Okay, again, this is very useful. And now think about 3-dimension, and later even 4-dimension maybe. What's the projection of this one? Okay, onto this vector. Can you see it's super difficult if you want to do it in terms of geometry? You have to move this one to here and somehow calculate the size and start to draw the triangles, and finally starting from this point and do a perpendicular drop line to this thing, which is going to be a 2-dimensional triangle in 3 dimensions, which is super difficult. But if you know vectors, super easy. That's nice. All right. That's the idea of projections. So finally, one application, work. This is not a physics class, so I'm just going to do it really quickly to show you how to calculate work and why we need a dot product. Okay, so in elementary physics, we know the definition of work. Say you have a cart, or maybe you have a table. You push it with a 20 Newton. Okay, and maybe this one, when you push it, moved for 30 feet. So during this time, you did work. You consumed energy. And work is simply the force times the distance. Okay, that means you need 2 components. If you use a very big force to push for the same distance, you do more work. If you use the 20 Newton to push for 60 feet instead of 30 feet, you do more work. You double the work. If you push something but that thing doesn't move, you spend effort, but you didn't do any work because it didn't move. And if something is moving, but you're not making effort, for example, you sit on the cart and the cart is moving, do you do any work? You don't, because you don't apply a force in the direction the cart is moving. Okay, so work is basically force times distance. The unit we can use feet times pound if you use pound and feet. But the standard international metric is going to be joule, which is meter for distance and Newton for force. Okay, let me write it down. Meter times Newton for force. Depending on which unit you're using, you are going to have different numbers. Okay, so that's the work, something we knew before. Now things become interesting. Now you're pushing the cart. You are pushing the cart with a 30-degree incline. So technically, you should also push in this way, right? But let's assume you're not able to, at the beginning, you're not able to get below the case and start pushing it in the direction you want. So instead, you just blindly push it horizontally, okay, with a 20 Newton. Let's do 20 pound. Now, from here you can see this one will still move. Well, the only problem is your 20 Newton pound of force is not fully contributing to the work in the direction this one is moving. Only part of it go to that. Sounds good? If you think about it, this force can be decomposed into two parts. The first part go along the incline, which is doing the work. The second part is totally wasted. So of course, the whole 20 pound force will not be applied to the distance, only part of it. Okay, so with that in mind, how do we calculate work now? Still quite simple. If this is where the distance is, and this is where the force is, and remember this time we care about directions, so these two things suddenly become vectors. Okay. Now, this force is not contributing to the distance, only this part is. So the work should not be the force times the vector, times the distance. It should be the force, but only the component which is in the direction of d times the distance. Okay, where theta is the angle between them, and from here you can see this is what? This is f dot d, exactly. So if you have a work, you have a force, you have a distance, they're in different directions. Or even if they're in the same directions, you just take theta to be 0. Okay, you can simply take the dot product to calculate the work. So if you think about what's going on here, 30 degree, and if you end up pushing this one horizontally with 20 pound, and this one ends up moving for 30 feet along the incline, how much work have you done? And of course, it's not going to be 20 times 30 equals 600. It's going to be less than that, because part of your effort is wasted. All right. So what's your force? 20, 0. What's your distance? My distance is going to be 30 in terms of length with a 30 degree. So if you draw the right triangle and find the coordinates, it's going to be 30 cosine 30, 30 sine 30, which give you 15. So the total work plus 0 times 15. Okay, so roughly 520, which is certainly smaller than 600. From here you can see, well, what you did is nothing but decompose your force into horizontal force and the vertical force. Horizontal force and the vertical force. Horizontal distance and the vertical distance. Okay, and then horizontal dot horizontal and vertical dot vertical. Since my force does not have any vertical contribution, so all the distance moved, which is 15, are wasted when I'm not helping that. So the real consequence of my work is I push something with the horizontal force, and even though that thing moved for 30, but it only moved 15 square root of 3 horizontally, I should only count that part of my work. Okay. So you can see dot product is nothing but decomposing a motion into the horizontal part plus the vertical part. That's the beauty of dot product. All right, that will be all for dot product. You will see all kinds of questions and problems and challenges in your textbook homework. Bring them to the discussion. This part may need a little bit more exercise, not on the dot product side, but on how to use dot product to solve real life problems. When you see a problem, you need to realize it's a dot product problem. And most of the cases, it's either related to too bad. Where is it? Okay. I would say it's either related to angle or maybe related to projection. And of course, because of that, we have work. So for these three cases, when you see it, that's when you probably want to start to think in terms of dot product. Because dot product is really good at handling all these, and that is because it has cosine theta in it. It has a much simpler way to deal with cosine theta compared to the law of cosine. All right. That will be all for this section, and that will be all for chapter 9.